Why wood poles for overhead systems? Presented by the North American Wood Pole Council. This presentation will review why we continue to use wood poles in North America to carry electricity and communications across the continent. It also explores the use of alternative materials for utility poles and some key differences with traditional wood poles. We hope this will provide you a more informed understanding on overhead systems that can help properly compare pole materials. Wood poles are the essential backbone of the North American electrical distribution system, carrying power and communications to hundreds of millions of citizens throughout the continent. We have more than a century of experience in using wood poles in overhead systems. While the electrical utility industry has evolved significantly over the past 100 years, the use of wood poles continues to offer unmatched benefits, both practically and economically. In North America, you can find wood poles delivering power to nearly every corner of the continent. Today, there are more than 150 million wood utility poles in service in North America. Each year, another million wood poles are installed, either in new construction or in replacing poles at the end of their service life. Let's look at the history of wood poles. The first wood poles were used for telegraph wires in 1844. Initially, the wires for the new telegraph were placed underground. However, those lines were fragile and failed repeatedly. So, with a $30,000 grant from the U.S. Congress, some 700 straight and sound cottonwood poles were purchased to carry the wires between Baltimore and Washington, D.C. In the next few decades, wood poles carried telegraph wires, often placed next to rail lines. At the turn of the 20th century, the electricity industry emerged, and with it, the need for more durable and larger wood poles. This led to wood treating standards developed by the American Wood Protection Association, or AWPA, in 1904. Round timber standards defining the strength of wood poles were developed in 1908. This in turn evolved into more specific structural standards for poles under the American National Standards Institute, or ANSI, in 1924. Over the decades, all of these standards have evolved and remain in place today. Treating standards used for protecting wood poles are maintained by AWPA, defining the preservatives that can be used and the proper practices to ensure durability. ANSI Standard 05.1 defines the sizes, classes, strengths, and other information necessary for designing overhead systems using wood poles. Lastly, there's the National Electrical Safety Code, or NESC, which defines the requirements and conditions for all components in an overhead system. Together, these three standards guide utilities in designing wood pole overhead systems that are durable, resilient, and effective. While some say wood poles are outdated here in the 21st century, such statements ignore some basic truths about wood poles that are as important today as they've ever been. First and foremost is cost. Wood poles offer the best value to performance benefit among all materials in both initial cost and in maintenance over its long service life. That cost benefit is well documented through the many decades of service provided by wood poles. We have a long record of in-place performance of preservative-treated poles where the service life can be extended to 75 years or more. Wood is also a unique material with a high strength-to-weight ratio, lack of conductivity, and natural variability that makes it resilient to extreme conditions. Through research, testing, and development of new technologies, we've learned more about the structural capabilities of wood poles, which are reflected in standards such as ANSI 05.1. Unlike other materials, should wood poles begin to deteriorate in service, this damage can be halted through a variety of proven remediation methods. Wood poles have a long documented history of longevity and service of up to 75 years or more, depending on the environment where they are located. And a regular program of inspection and remediation can extend this service life by as much as 25 years. One often overlooked benefit is the wood treating industry's ability to supply poles quickly after a natural disaster, such as a hurricane or ice storms. With wood pole manufacturers located throughout the country, these plants can increase production and supply poles to utilities to quickly restore power. For example, following Hurricane Katrina, the wood pole industry supplied 92,000 poles and 90,000 wood crossarms within 4 weeks. No other material offers this supply ability. Utility linemen love wood poles because they can be climbed easily with very little equipment. This is critical in repairing and restoring power. Also, the fact that wood poles don't conduct electricity is a key safety factor for line workers. Wood poles come from a renewable, sustainable material, trees. Through modern reforestation and harvest practices, North American forests continue to grow far beyond the volumes harvested each year. With the long service life, new trees can be grown to become replacements over the decades of long life for the pole. Wood poles have a significantly lower impact on the environment in production and use, as detailed in science-based life cycle assessments, or LCAs. Also, trees remove carbon from the atmosphere, and wood poles lock in that carbon for decades, far beyond the natural life of the wood. The function of a utility pole is to hold up the lines, transformers, and other equipment needed for electrical distribution. So invariably, the discussions about material used to make a wood pole becomes a debate on the structural capabilities of that material. Too often, these debates are centered on bad information or misleading comparisons offered by promoters. It's best to pull back the curtain and take a look at the deeper issues when it comes to utility pole materials. It's important to recognize that no material is failure-proof. Utility poles may be exposed to conditions that are far beyond their structural capacity. That's not to say that we can't make poles that can withstand tremendous forces. However, it prompts the question, at what cost? For utilities, they must contend with balancing the costs against the benefits of much stronger poles, as funding for overhead systems is finite. That means accepting some risk of an extreme event versus the increased cost of a higher strength pole. So when comparing wood poles against alternative materials, there are a number of things that should be considered to be able to make an informed choice. Too often these considerations are neglected in the rush to promote other materials. A common misperception is that composites, steel, and concrete are stronger than wood. But any engineer can tell you that is false, as the structural capability is based on the design, not the material. The reality is you can find a pole, no matter the material, to meet the typical overhead system loads. Another consideration is the difference between wood, a natural material, and alternatives, which are extruded materials. With wood, we basically remove the bark and then integrate preservatives into the wood. The structural capabilities of the pole are based on what nature gives the tree, including any imperfections that impact the strength. With extruded materials, those imperfections in the material can be controlled better. When standards were created for wood poles, the natural variations of wood were incorporated when determining strength values. Safety factors were added to accommodate the variability in wood, resulting in a higher coefficient of variability, or COV. For wood, that variability is 20%. Alternative materials have a tighter COV of around 5%. And I'll explain why that's important in just a moment. Lastly, Many promoters of alternative materials create comparisons of their poles to wood in ways that are not equal to argue why theirs is stronger or better. We found many unequal comparisons, particularly made by fiberglass composite promoters, that do not stand up to engineering scrutiny. While it's a bit of an oversimplification, the overall strength of wood poles is determined by their size. The bigger the tree, the more load it can carry. That led to establishing classes for wood poles. Now, this table from the ANSI 05.1 standard shows the sizes for each class measured by the length of the pole, the circumference at the top, and the bottom circumference, which is measured 6 feet from the butt, where that section will be buried in the ground. Also defined is the specific distance the pole will be buried. For this, the larger the pole, the deeper it will be buried, and the ground line will be further from the butt. To illustrate this, for a Class 3 Douglas fir or southern pine pole 40 feet in length, the top circumference is 23 inches and the bottom is 36 inches. For a much stronger H1 pole of the same length, the top would be a minimum of 29 inches and the bottom 43.5 inches. That extra 6 or 7 inches is key when it comes to assigned pole strengths. For wood, as the tree gets larger, it also gets stronger through the circumference effect. For example, if you increase a pole from a 26-inch circumference to a 34-inch circumference, you have a 30% increase in size. However, the assigned bending capacity with that extra 8 inches in circumference increases by some 123% or more than double. The reason for such an increase is that up to 90% of the pole's bending strength is in the outer 2 to 3 inches of the pole. As the tree grows, branches fall off the bottom sections. Branches are knots in a tree, so as the tree gets wider, the wood fiber has fewer imperfections and thus is stronger. Because no tree is exactly the same, there is a wider variation in strength capacities. In a population of poles of the same size, there will be a few that are weaker and a few that are much stronger. This bell curve illustrates the distribution strength in natural wood. Now, when strength values were assigned for wood poles, they were not set at the midpoint, but instead were placed at the lower end of capacity. In most cases, the rated capacity may be as much as 2.5 times lower than the average strength value, or where 95% of the poles will handle the load. This ensures that a vast majority of poles will meet or exceed the rated loading. Because of this variability, wood poles have a unique overload capacity not found in alternatives. Let's look at why that's important. First, here's a wood pole and its distribution of strengths. With a conservative assessment of strength properties, the assigned strength value for the wood pole is on the low end of this distribution. Now, you can specify the wood pole to meet such a load condition as shown here, or you can then specify a fiberglass or steel pole with a similar rating but with a lower coefficient of variation. All of that works until you have an extreme event such as a hurricane or excessive ice. When the load exceeds the rating of the alternative poles, they will likely fail because they are not designed for that event. While the wood pole may fail as well, given the strength variation, there is a much higher likelihood the pole is strong enough to withstand the extreme condition. The ANSI 05.1 Wood Poles Manual has all the information needed to calculate design loads. NAPOC also offers a manual, Wood Pole Design Considerations, written by an engineer that details how best to design with wood poles. Recently, scientific papers have appeared attempting to show how alternative poles are better than wood. However, a closer look at these supposedly science-based claims are not as objective as they purport to be. For example, this report in a Canadian journal concludes that in hurricane wind loads, out of 1,000 poles, 400 wood poles would fail, while virtually all composite poles would survive. But digging deeper on how they reached this conclusion uncovered some questionable research. First, the study compares western red cedar wood poles, which have the lowest strength values, against composite poles that were rated significantly higher. It further misapplies design factors for the wood poles, clearly defined in the standard. This leads to misleading bending strengths that make the composite poles look stronger. We contacted the study authors and pointed out the many errors in their calculations and methods. They issued a revised report, but failed to correct key design errors. Instead, they just changed the conclusions to more non-specific statements about the superiority of composite poles. The North American Wood Pole Council has published a detailed review of this study, underscoring the specific errors in the calculations and the conclusions. And it's available on the woodpoles.org website. There are applications where alternative materials may be better suited for specific applications. However, broad, unsupported claims about structural superiority do not stand up to scrutiny, and these fail to take into account on what the root causes of pole failures. Officials with the National Electrical Safety Code a few years ago looked at what causes overhead system failures, and what they found was unexpected. A great number of the failures were not because of wind or ice that brought the poles and lines down. Instead, secondary damage such as trees and debris falling onto lines and poles and other debris caused more failures. Further, a study in Florida found that overhead components such as transformers and line connectors failed at a much higher rate than poles. So simply installing bigger or higher strength poles may not offer the resiliency that utilities desire. Another important consideration in choosing pole materials is the life in service. How long will a pole last in place? Utility poles must withstand a wide extreme of environmental conditions, from blazing deserts to harsh winters, and they must endure these ever-changing conditions for decades. Now, there are many factors that come into play when it comes to determining how long a pole will remain in service. Certainly, the loads placed on a pole can impact how long it can last in place. As you see, over the decades, we've learned a few things on how much we can put on a pole. In terms of specifications, it's important to specify the right pole for the expected loading conditions, taking into account the risk for extreme loads the pole may experience in service. The environment and weather conditions where a pole is placed can affect its longevity, particularly for wood poles. In dry, desert climates, wood poles face lower risks of deterioration with a lack of moisture that can promote decay and insects. In warmer, more humid conditions, there is a higher potential risk of deterioration. Northern regions that experience snow and ice may see conditions that do impact service life. Now, the environment affects other materials as well, through risks of ultraviolet light exposure, high pH levels in soil, and other factors that may impact fiberglass composites, steel, and concrete. Maintaining your pole plant, no matter the material, is essential to the longevity of your poles. North American utilities have discovered the value in implementing regular inspections on poles, identifying potential damage early on. This can lead to remediation that can further increase the time the pole can remain in service. How the poles are made can determine the length of service as well. The quality control standards for treated wood poles have evolved over the century, leading to consistent, proven practices to make long-lasting poles. Universal standards for other materials don't necessarily exist, so buyers must rely on the commitment of the supplying company in producing a quality product. For wood poles, assessing the service life can get mixed up with other unrelated practices. For example, alternative promoters often note that wood poles only last 30 years. However, that is based on an assessment of the asset's value in a utility's finances, basically how long that asset, the pole, can be depreciated. So that 30-year lifespan has no relation to the actual physical condition of the pole. There are other more specific assessments on wood pole life that are based on actual conditions of the poles in service. Quanta Technology conducted utility surveys covering some 60 million wood poles across the U.S. Those surveys showed an average pole life of 53 years with no maintenance and up to 96 years with regular maintenance. The largest pole remediation company in North America, Osmos Utility Services, keeps a database covering some 750,000 inspected poles. They define the end of a pole's life as when it has 50% less than the NESC strength requirements. Based on their surveys, average wood pole service life was 45 years with no maintenance and 73 years with regular maintenance. Oregon State University, one of the leading institutions on wood durability, conducted similar surveys and determined that wood poles are replaced at a rate of 0.6% a year. At that rate, OSU researchers concluded that service life, quote, would easily reach 80 years in many areas of the country. Wood poles have the advantage of more than a century of use, so service life can be estimated on actual experience. By comparison, fiberglass composite poles have only been in use for the past 25 years. Yet promoters of these poles claim they can last as long as 60 years to even 125 years. Since they don't have actual experience in service, fiberglass pole makers offer estimates by mathematically extrapolating the results of ASTM tests such as accelerated weathering to support their service life claims. However, the science and engineering communities understand the limitations of laboratory tests versus actual experience. In fact, ASTM has a specific caution on that practice, stating, calculation of an acceleration factor relating X hours of laboratory accelerated test to Y months or years of exterior exposure is not recommended. One of the benefits of a century of using wood poles is the development of remediation methods and the documented value it can have in enhancing the longevity of poles in service. One truth that is often glossed over by promoters is that no material is immune from environmental damage. For wood, the threats are decay and insects such as termites. For fiberglass composites, the threat is in ultraviolet light exposure as well as impacts from temperature extremes. Steel can be impacted by corrosion as well as damage to the surface that impacts its strength capabilities. Concrete can be impacted by temperature extremes and moisture exposure that can cause spalling, with concrete losing its cohesiveness. The reality is that the environment where poles are placed is very demanding on any material. Wood poles are pressure treated to protect against decay and insects. However, that protection can lessen over the decades. So we have learned how to enhance that protection and keep poles in service. The key is in regularly inspecting wood poles to identify when decay or insect damage may be starting and apply remediation to halt further damage. These methods have been proven to increase the life of poles significantly. Studies done by Osmos Utility Services have documented the value of remediation on pole service life. Their analysis of hundreds of thousands of wood pole inspections has confirmed that remediating wood poles through a regular inspection program can increase the service life of the wood pole by 60% or more than 28 years. Research into new and existing remediation methods is continuing. Oregon State University's Utility Pole Research Cooperative conducts monitoring and new studies on pole remediation preservatives and methods. This includes analyzing test samples in place for decades to confirm the effectiveness of these measures with objective, science-based data. It's interesting that alternative materials to date have not developed similar remediation practices for their materials. In many cases, once the structural capability of a fiberglass or steel pole has been compromised, the only option is to replace the pole. When it comes to materials for poles, there are other things that should be considered when deciding what material to use. Utilities today operate under growing scrutiny about their impact on the environment, from the sources of energy to the materials that they use. Wood poles offer many more environmental benefits compared to alternative materials, from renewability and sustainability of wood to carbon sequestration and the impacts on the environment when viewed from a life cycle analysis standpoint. Wood remains the only truly sustainable material for utility poles. A tree starts as a seed in the soil that over decades grows and takes in water, sunlight, and carbon dioxide. With proper forest management, these trees provide oxygen, wildlife habitat, recreation, and a resource for wood products such as poles. At the end of its life, the wood breaks down into organic material to start this cycle all over again. Through preservative treating, we can make that wood last far beyond its natural life. So much so that we have time to grow a new tree that can become a replacement when that pole comes to the end of its service life. One key benefit that has emerged recently is the role wood poles play in removing carbon from the atmosphere. Trees convert carbon dioxide into carbon, which is wood fiber. That carbon remains in place until the wood is broken down into organic material when it is released back into the atmosphere. By making wood poles last for decades, we are holding or sequestering that carbon in place for much longer. We've developed an online carbon calculator that allows utilities to assess their pole plant and determine how much carbon is sequestered in their system. Once they calculate the volumes, there are links where they can quantify that benefit in real-world terms. For example, the carbon sequestered from the atmosphere in 2,000 H1 60-foot poles is equal to the emissions generated from driving 10.8 million miles in a passenger car. A life cycle assessment on treated wood poles versus alternatives shows wood poles require less total energy, less fossil fuel, and less water than concrete, steel, and composite fiberglass. These assessments are cradle-to-grave look at these materials. In 5 out of 6 key indicators, wood poles have far lower impact on the environment in terms of water and energy use, as well as emissions of greenhouse gases, acid rain, and ecotoxicity. Wood poles have been and continue to be an essential component delivering power and communication to every corner of our continent. For more than a century, both utilities and the wood pole industry have adapted to changes to create an electrical grid that is one of the best in the world. With modern management and regulations in place, North American forests will continue to provide the resource for wood poles now and in perpetuity. Wood poles were a good idea to carry power 100 years ago, and they continue to be a good idea here in the 21st century. All of the information presented today and more on wood poles is detailed in the website woodpoles.org. This is the largest website on wood poles in the world. On this site, you'll find an extensive technical library of publications on wood poles, as well as a host of online calculators, educational materials, and digital tools supporting these critical assets. Thanks for watching. For more information, please visit our website at woodpoles.org.